So now I'm going to introduce a new thermodynamic quantity for us, which is known as Gibbs Free Energy. And this is a rather elusive term, the free energy. So first I'm going to talk about the mathematical definition, and then more of the conceptual definition, like what does that mean, free energy? Okay. So we use G for Gibbs, free energy. And by definition, so this is like our exact definition of Gibbs, it is H minus T times S. Okay, so that is enthalpy minus temperature times entropy. Okay. And similarly, if we're interested in the change in Gibbs free energy, and this is really what we want, that's our desirable quantity, then I can tack on a delta for the enthalpy and I can tack on a delta for the entropy. And I don't need to tack on a delta for the temperature, because what I really want to see with Gibbs free energy is what is the change in Gibbs free energy as the result of a process such as a chemical reaction or even a phase transition at a specific value of temperature. Okay? So that's what it is mathematically. So what is this conceptually? Well, Gibbs represents the difference between temperature-weighted entropy, so all I mean by that is temperature times entropy, minus enthalpy. So this can be thought of as the difference between heat flow and the number of arrangements available to the system. So think about that. We've got now the difference, right, between the heat of the system and the number of ways that the system can be arranged. The difference between those two quantities, delta G, that represents the amount of free energy the system is available to do as work. And the type of work we're talking about here is chemical work. Okay, so more on this, because I know this is rather confusing. So let's keep going down this line, okay? And so I'm going to play some tricks with algebra over here. So if we have our equation, delta G equals delta H minus T delta S, and just playing with some algebra here, if we divide both sides by negative T, so let's just do that, then we get this equation down here. So now I've got negative delta G divided by T, which equals negative delta H divided by T, plus delta S, so the sign changed on delta S. So what's happening with this whole thing? Well, I'm going to rewrite that down here, okay? And this time I'm going to tack on system to each of these quantities. So now that's delta H of the system over temperature, and we'll talk about that temperature here momentarily. And now this is delta S of the system, okay? Well, if we recall that the entropy change of the surroundings is negative delta H of the system divided by, of course, the temperature of the surroundings. And so we can put that on there. Then that means this whole quantity is actually the entropy of the surroundings. Okay, right? And so I could tack that on to there as well. And so now if I was rearranging this, what this is, this delta S or delta H of the system divided by temperature of the surroundings, I'm just going to replace that with delta S surroundings, right? And that's still plus delta S of the system. And so we recognize that delta S surroundings plus delta S system is just the total entropy, right? So we can say negative delta G specifically of the system divided by the temperature of the surroundings is another way I could calculate total entropy. So what does this mean? Okay, well, we remember that delta S total must be greater than 0 for all spontaneous changes. So if something is spontaneous, it must have a delta S total greater than 0. Well, Well, now we see this relationship between the delta S total and the free energy of the system. And we can see that they're the opposite, right? There's a negative sign right there. So that means if delta S total is greater than 0 for all spontaneous changes, that means the free energy of the system must be less than 0 for all spontaneous changes. So this gives us another way of looking at spontaneity and only focused on the system, right? So again, if we have a spontaneous process, its total entropy must increase and its free energy must decrease. And that decrease of free energy, we could kind of think of that in some ways as like exothermic work. So I'll put that in quotes here, exothermic work. And so what that means is our system has free energy to use, right? Because that delta G is negative, what that means is our system can use that energy on the surroundings to perform a task. And that task is more likely like a chemical reaction, right? And so, of course, we can calculate the standard free energy of a reaction using the exact same formula that we did last time, okay? And this is going to help us assess if a reaction should be spontaneous, all right? So let's do this calculation, and I'll record this in a Part B video.